Okay, Bismillahirrahmanirrahim. So now we are going to discuss the possible ways for the radioactive decay. And again, you have reached to this point, and we started with the chemistry of the nucleus, and then we actually discussed the stability in terms of the binding energy, and later on we moved to the different nuclides and to decide their stability with respect to the neutron and the proton ratio. Now we are moving to the more focused area, because our concern is if the nucleus is unstable. So unstable mean if it is the radioactive, then if it is a radioactive, then they have the tendency to be stabilized, and when they are going to be stabilized, that means they will emit some sort of the decays, and or you can the particles or the rays, and these are the different forms of the radioactive decay. It is the alpha decay, negatron emission, positron emission, electron capture, and gamma decay. So these are the five of the major radioactive decay, and objective here is to learn when the nuclides are going to emit these type of the radiation, and how they are going to be stabilized. What is the reason if they are going to be stabilized with the emission of the alpha, neutron, positron, electron capture, or the gamma radiation. So briefly, what we are going to cover in this lecture. So this is just the objective I have mentioned over here. So we know you are going to learn the type of the radioactive decay, and what are the actually their nuclear reactions, and what is happening with the parent to the daughter, and what actually is the change in the mass number or the atomic number or the change in the energy. So this is our main objective. So when you learn all these objectives, then you will be able to decide if the nucleus or the nuclide is unstable, what it should emit the radiation alpha or gamma or beta or the electron capture, and this we will decide at the end of the lecture, after learning all these different type of the radioactive decay. So one important point over here is generally we label the unstable nuclide, it is the parent, and after decay with the sort of the different type of the radiation, it is converted to another nuclide, and that is called the daughter nuclide. So these two terms I will be frequently using during the course. So remember, whatever it is the starting the nuclide, it will be called as the parent, and the after decay or the nuclear reaction, the nuclide is going to form, that is called the daughter nuclide. So this is the parent nuclide, and we call them the daughter nuclide. So today I'm going to teach you the alpha decay. So there are not only we are going to discuss the alpha decay actually, because this is a little bit advanced course. So we are going to calculate the energy release in case of the alpha decay, because there are a lot of the nuclear reactions. If the alpha is being emitted, then what would be the possible energy is being released in case of the alpha decay, or whether you can decide whether this is the exoergic reaction or the endoergic reaction. So this is the different terms, but they have the same sense as we use in the chemical reaction, exothermic reaction or the endothermic reaction. So all these we are going to cover in by studying the alpha decay. So the first, have a look in the general. This is the general picture. So what is happening, as I have said, if it is a parent, and after the decay of the alpha particle, it is converted into the daughter nuclide. So this will be happening for all type of the decays. There should be one parent, and it is converted into daughter with the emission of the decay. And here it is one of the example is the alpha particle. So I'm taking as an example, and there are a lot of the nuclear reactions. You can pick up all these nuclear reactions from the online sources, and I have shared with you my book as well. You can find there many of the nuclear reactions. So this is the actually protactinium. It is converted into the this is sorry, this is not the Neptunian. This is the Neptunian, and it is converted into protactinium, and with the emission of the alpha decay. So it is very important to have a keen look over here. That means what is happening actually in this nuclear reaction. So this may be, you call it is a alpha decay, or it is sort of the reaction. That means this is the reactant converted into the products over here, similar to what you are going to study in the chemical reactions. So in each of the alpha decay, when there is alpha decay, of course, one is important part over here is the alpha. Alpha is emitted, that's why we call it the alpha decay. So the first part and the main thing to understand over here is, and as we are learning from the start of this course, as the nucleus is composed of with the protons and the neutrons. So actually, there is changing with the number of protons and neutrons in the daughter as compared to the parent nuclide. So what is happening over here? This is a general equation. That's what this is the x. X over here is the Neptunium, and you may label any of the x. Again, I don't expect to memorize all these nuclide. Whenever there is a difficulty to understand the actually what be the atomic number or mass number of any of the nuclide, so you can put just the x. So important here is the to learn the objective, to learn the main points which we are going to cover under the heading of the alpha decay, not to memorize in your mind all these the values of the atomic number and the mass number. So again, if it is another particle, you can put the y over here. So this is the general equation. So important over here is this is the alpha. Alpha is being emitted, and this is any of the nuclide, and this will x will be called the parent nuclide. So this is the parent, this is the parent, this is the parent nuclide, having the atomic number and the mass number. So this is the number of protons, and you can calculate the number of neutrons after subtracting the z from a. The, these will be the number of the neutrons. So number of protons and neutrons are important over here, or you can say atomic number and the mass number is also important, because in mass number the number of neutrons are included. So when it is emitted, so what is happening? Actually, in chemical reaction, you are balancing the number of the molecules on the both sides. How many molecules are taking part in a chemical reactions, and here in nuclear reaction, in all type of the nuclear reaction, actually we are going to balance the atomic number and the mass number. So if this is the Z atomic number, so of course, no, if it emits the alpha radiation, so there is the decrease of the two atomic number. That's why whatever is the daughter, it must have Z minus 2. That means two atomic number is less than as compared to the parent. And in a similar way, because the mass number over here is the 4, so whatever it is the daughter nuclide, its mass number must be less than as compared to the must be less than 4 as compared to the mass number of the parent nuclide. So this is example given over here. If you have a look, that means on the both side you must have to balance the atomic number and the mass number. That's for here it is a 93, 2 is over here, and 91 plus 92, that is the 93, and in a similar way 233 plus 4, that will be the 237. So this is the very simple way. If you understand only this alpha decay, automatically you can understand the rest of the nuclear chemistry. So actually, uh, this is the way you can learn by using a single point, and then we will move to the higher content of this course. So important over here is this is the not the only case the change in the atomic number and the mass number. And what is happening actually, there is some sort of the energy is being released over here. That's why it is on the side of the product. And in a similar to the chemical reactions, if it is the energy on the product side, that means energy is released, and where you can call them the exothermic reaction. But here is the different terms we are going to use. I am going to explain later on. So the first, have a look, how can you calculate the this Q value? And this is again very simple, very easy to calculate the energy release in nuclear decay. And even in the case of the alpha decay, and the energy equation is, this is called the disintegration energy. And the value of Q would always be the positive. When it is positive, it is the spontaneous decay. And this can be calculated by using the simple Einstein equation, which we are using before to calculate the binding energy of the nuclide. So important point over here is this is the positive value, and this the sign is in contrary to the chemical reactions, because if the sign of this in chemical reaction is minus, then we call them the exothermic reaction. The reaction is the spontaneous. But here, look at what is written over here. The value of Q is positive. That means this is the spontaneous reaction. So when the value of Q is positive, that means the energy is released. So what is the reason why it is having the opposite sign? I am just moving towards this question as well. So first, have a look, how can you calculate the value of Q? Again, it is very simple. This is the same equation we are using. That means E is equal to Q is equal to mc square. This is the Einstein equation. And in the binding energy, we use the whatever it was, the calculated mass minus the uh, actual mass. So the difference in energy, then you just multiply the 931.5 to convert into mass into energy. And the same way we are going to proceed over here. That's why I said before that conversion is very, very important. We are not going to use all detailed calculation each time. So what we are going to do over here, so look at the this one equation. Actually, this is the difference in mass. So what is the difference in mass? This is the mass of X, and the mass of X is the, that means the mass of the parent. And this is the mass of Y. Mass of Y is the daughter, and minus mass of alpha. Alpha is over here. So simply, actually, this is the mass of the reactant minus mass of the product. So in the reactant side, there is only one nuclide, because this is the alpha decay. And on the product side, there are two nuclides. One is the alpha, other one is the daughter. So alpha and daughter are given. So what you are going to do over here, you are just subtracting the mass of the daughter and the alpha from the parent, and then you just multiply by 931.5 uh, to convert this mass into energy, and you can find this the value of the energy released in the alpha decay. And this is very, very important. So now as a chemist, you can calculate actually what is the energy release in all cases. It doesn't mean this Q value will remain same. It is going to depend on the parent as well as the daughter, because here what important point is, this is the constant, but the mass of the parent and daughter also matters for the calculation of the Q value. So moving to the now I'm going to explain over here, and because this is the first the point we are going to use these terms. So again, we are going to use the term exoergic instead of the exothermic in case of the chemical reaction, but in the nuclear reaction, we will use the term exoergic. Exo mean released, so energy released If energy released, that is called the spontaneous. So this actually the term is the same as you are using for the chemical reaction, but the only difference is over here is the it is having the positive sign. In chemical reaction it is having the minus sign. So what is the reason? The reason is, uh, first, in the chemical reaction it is the minus sign because there you subtract the difference of change in enthalpy or the energy from product from the reactant. That's why the sign is the minus. But here, the way of calculation is reactant minus product as given over here. This is the parent minus daughter and the alpha particles. So that means in a reverse way, you are going to calculate the difference in masses. So that's why here the sign is opposite. So this is only the reason. Otherwise, whenever it is a exo, whether this is the chemical reaction or the nuclear reaction, exo mean energy release, and that should be a spontaneous way of the reaction. And similar to the other one, if the sign is negative, and we call it the endoergic reaction or the decay, and it would be a non-spontaneous. Again, the reason is I have already explained in this uh, way, uh, in case of the positive sign. So opposite to the this, of course, if it is the minus sign in chemical reaction, you can say it is an endothermic reaction, and endothermic are also non-spontaneous. In nuclear reaction, we call them the endoergic reactions or the endoergic decay. These are also non-spontaneous, but only the difference is the sign. Here the sign is minus. In chemical reaction, it must be a positive. And the reason is the way of the calculation from product minus reactant in chemical reaction, and in nuclear reaction from reactant minus products. So this is the only the reason behind this, the calculation of the Q. So let's see another example. So again, what is the way of learning over here? This is the radium is converted into the radon. Maybe in your examination, I may skip this one, I may skip this one, or I may skip this one if I say what would be the form of the alpha decay. And you have to just the balance the number of protons on the neutrons each side, or the atomic number or the mass number on each side. So here, if it is converted, that's why if I'm not showing over here, this is the radon, and if it is the alpha decay, only this parent and the decay is given, you can easily fill up what would be the rest of the nuclide, because here 88 and 2 are there. That means 86 should be there. So this should be 86 plus 2, that would be equal to 88. And in similar, it is 226 because this is not given, and only helium is given. So 4 mean you have to add 220 to into 4, that will give you the value of 226. That means you are having a daughter nuclide having the atomic number of 86 and mass number of the 222. So this Rn, again, for me the symbol is not important, and what is, you can put over Y over here. If you do not know the what is the this elemental, the symbol for the nuclide having 86 atomic number, so better to put the Y. So don't put any wrong element with the wrong atomic number, because whenever it is the 86, it must be a radon. There is no element which is having atomic number 86. So it is better to use the correct element. If you do not know, then better to use the Y over here or X over here. So that is the okay. There will be no any detection of mass. So let's see another example. So these are the similar examples. Let's suppose now I am going to just the skip. This is the parent nuclide uranium is converted into the thorium and the helium again. This is the alpha decay. Let's suppose if I am going to skip this one. So you can also write down what would be the parent nuclide, because here again the uh, in the product side there is atomic number 90, and it is 2. That means the parent should be 90 plus 2, it should be 92. And the mass number over here 234 plus 4, that is total is the 238. That means the parent must having the mass number of the 238. So these are the different way you can balance the nuclear reaction in case of the alpha decay. And you can also put if one of the parent or the daughter or the alpha is missing over here, you can put the any of the missing nuclide by using or by balancing the total number of the protons or the atomic number and the mass number. Now we are moving towards the calculation. How can you calculate the energy released, and how can you decide whether this decay is the spontaneous or non-spontaneous? So of course one of the actually the understanding is if it is going to be decay, it must be a spontaneous decay, because nuclides doesn't need any help to going to be disintegrated. It must be a spontaneous decay. And if it is the spontaneous decay, the value must be positive, as we have discussed before. So this is another example. When this is the plutonium is converted into the uranium, the mass number, there is another nuclide having the mass number 235, and this is the helium. Again, for the calculation of the Q value, there is no need for the atomic number, because we are only concerned with the mass, the reference mass, because we are using this equation, and there is only need what will the difference in mass of the parent and the nuclide. So the use of the number of protons are there just when you are going to decide actually what would be the possible nuclide after the decay of the parent into the daughter. And then of course you will need the number of the protons or the atomic number. So simply, if this is given, the mass of plutonium is 239.05216, and mass of uranium 235 is this, mass of helium is 4.00260. So what is happening? This is the mass of the parent, and this is the mass of the daughters. So as we use the equation, so that means this you have to subtract from each mass. So that's why this is being done over here. This will be positive, this will be negative, this will be negative, and this is the differences mass. Actually, the reason for the energy release in similar to the binding energy, so this mass is lost, and actually this is not going to lose as per law. It is converted into the energy, and this is a factor 931.5. You can multiply this one and you would get the value. It is the plus 5.24 mega electron volt. That means this is the energy release in case of the alpha decay when uh, uh, plutonium is converted into the uranium 235. And again, nuclear uh, chemistry, the mass number are important, and you can say that because there are the different nuclides, the same isotope having different mass number, so it is better to use the term plutonium 239 is converted into uranium 235. It is going to be the energy of 5.24 mega electron volt. And now you are going to decide whether this is the spontaneous or the non-spontaneous. And of course, the value is positive. It is called the exorgic reaction or exorgic decay. So this is the spontaneous decay. So based on this information, you can decide any of the alpha decay. Let's suppose you can assume if this is converted to another nuclide after the decay, and then you can calculate the energy release. If energy release in minus, that means this way of decay is not possible. The only possible way is when you are having a loss in mass, and you must have the positive value of the Q value. That means the energy release in the decay. So of course, This is the exergic reaction and it is the spontaneous. So now again I am now giving you one of the example, and you can calculate right now what would be the energy release in the alpha decay, and what how can you decide whether this is the spontaneous decay or the non-spontaneous decay, and the values are given over here. So you can calculate, and with the same way I have calculated before, and after this you will just raise your hand. I will be calling your name to check the values. So what is it? Again, this is a simple calculation. You are just adding the two masses and subtracting with the parent. There is no any complex calculation over here. So the value is, this is the mass difference. You are going to multiply with the 931.5. So this is the with this factor, and the value would be 13.29, and it is the positive value. It is the spontaneous decay. So this was my question, and the answer is here. So again, if still there is need, don't worry about this one. Just do the practice, because this is only you can do. Otherwise, if I am teaching and lot of other data is available, you are not going to learn unless you will do yourself. If it is a basic one, you are unable to understand. So just focus on your weakness. It is not the discussing point, but everybody should take a lead and, of course, cover up their weak point or the. So this one is the last slide. I have recorded this one. Maybe you can watch again, and in a similar way, you can calculate the Q value and decide why it is the spontaneous or the non-spontaneous selection. You have to give the reason, and the reason is same as I have explained in this video. So it is recorded. You can watch again, and this is all about our today lecture.